So in the last class, we were talking about conservation of leptons. Earlier class on new particle physics, we were talking about conservation of leptons. If you find anything that I am saying is very strange and not you can't understand anything, at least you have to come and tell me. I have been talking about conservation laws in the sense that I have, let us say, if I have a process A plus B going to C plus D, this is an elementary particle process. Where all these A, B, C, D, they are all elementary particles. Any elementary particles. Does it happen? That's the question we are asking. If I ask that, that is a vague question. I'm telling you when it will happen. So that for that, I have to know what are the conservation laws. That is based on conservation laws, I can tell whether this can happen or it doesn't happen in nature. So that has been our goal from day number 1 in particle physics. So we had told you momentum conservation, energy conservation, etc., etc. We now graduated to talk about some conservation laws which are beyond space-time conservation laws. One of them that I told you is conservation of charge. Conservation of charge is a symmetry. It is called U1 gauge symmetry. That is, if you very specifically, if you want to know, it's called U1 gauge symmetry. And then number 2, I have what is called as, yes, any question? So 2, I will say conservation of baryon number. Conservation of baryon number says if A has a baryon number B, BA, B has a baryon number, and then BC, BD, it should be equal. That is what is said by baryon number conservation. So why baryon number should be conserved? There is nothing appealing to tell you that you have some conservation law because there is a symmetry associated with it. Because I can't see through my eyes, I cannot see the symmetry. I will say this is some symmetry, some gauge symmetry. I don't know what it is. Gradually, people will start realizing what kind of a gauge symmetry it is, what is its mathematical structure. Similarly, when I said baryons, baryons are fermions. So why, if baryon number is conserved, why not lepton number? So for that, we had some arguments. Every conservation law comes with some process does not happen. Can I explain it? That's how we start. So I had told you, lepton number conservation says the total number of leptons should be same. In that case, I can check neutron decay process. I am repeating it now. Neutron goes into a proton plus electron plus antineutrino. Neutron has lepton number 0 because it's not a lepton. Proton has lepton number 0, it's not a lepton. Electron is a lepton with lepton number 1. Antineutrino is a lepton with antilepton. It is lepton number is -1. So it process is conserved. So we checked such processes. You have to now go ahead and check it again. Suppose you take the law of conservation law is good for leptons. I want to ask, can this process happen? That is, there is a process. Okay, I will not go through the whole thing. I will just tell you why not a muon decay into an electron plus a photon. Lepton number is conserved here. Angular momentum is conserved here. Everything else is conserved here. Why not a muon decay into an electron plus a photon? So to answer that question, we say that this is some kind of a mu-ness to lepton number, electron-ness to lepton number. And then I took a long time to explain you lepton number Le is 1 for the family of leptons. Family of leptons contains electron, neutrino, and an electron. For that, Le is 1, L mu is 0. Similarly, Le is -1, L mu is 0 for anti-electron, that is, sorry, anti-neutrino, electron neutrino, and a E plus. With this, we say theoretically that there are two different kind of neutrinos. Can I experimentally verify it is the next question. So our reformed law of conservation of lepton number says electron-lepton number is 0 for muon and nu mu and all other hadrons, photons, etc. And muon-lepton number is non-zero only for the muon family. So, and for the corresponding anti-muon lepton family, we have L mu is equal to 1. With that, we will check whether a given process has mu lepton number conserved, electron lepton number conserved, etc. For that, I gave you some typical examples also. Now, I skipped that because I have already told you about it. Experimentally, how do I verify? There are two different types of neutrinos. That is the agenda of today's class. It's a short thing, but you have to understand it. Storyline is to verify two different types of neutrinos exist. So that was done in 1962 by Lederman, Schwarz, and Steinberger. They conducted an experiment at Brookhaven to test the two neutrino hypothesis. That is, there are two different types of neutrinos, like nu E and nu mu. Two are there. So what they did is they used an intense beam of antineutrinos. Say, for example, flux of 10 to the 14 neutrinos per second. That is, they check. In any neutrino source, neutrinos are not counted. Any accompanying particle is counted. So when they count 10 to the power 4 particles associated with that, there should be 10 to the power 14 neutrinos may be there. So per second, in every second, you have 10 to the power 14 neutrinos. From in a pion decay, I take a pion decay, pi minus, going to mu minus and a nu bar. According to your lepton number conservation, what should I write for this nu? Nu has to have a suffix. Can you tell me what suffix should I have here? Lepton number for pi minus. Let me write it, because if I keep on talking about mu, nu, lepton and all that, you will lose interest. You have to involve yourself when I ask you a question. Otherwise, it's no use. So what am I saying? I have a process pi minus decaying into a mu minus plus I am writing a neutrino, let us say, or a pi plus decaying into a mu plus and just a minute, mu minus this, nu. Identify what is index, what type of a nu is this? Suffix of nu. That is it a electron neutrino or is it a muon neutrino? How do you check it? Check what is lepton number Le and L mu in this process. What is Le, left hand side? I'm asking a question so that you are involved in what I am doing. What is left hand side lepton number, electron lepton number for pi minus? I will keep quiet till you answer.
Zero.
Okay, pion is not a lepton, so lepton number is 0. Right hand side. Mu minus. What is Le for muon?
0, ma'am.
Okay. And nu bar, what is the electron lepton number?
1, ma'am.
How? Is it a nu? You are assuming that it is a nu E here, correct? Even if it is a nu E,
No,
nu
no.
E bar has a -1. What is Le for this? Now you should have a LHS is equal to RHS, no? If you have to have a LHS is equal to RHS, what should be the electron lepton number of nu bar?
0.
If conservation law holds. Now I come to L mu. So L mu has lepton, pion has a lepton, LHS has lepton number. What? LHS value for the lepton, muon lepton number for left hand side.
0.
0 equal to muon. What is the L mu value for a mu minus?
1, ma'am.
1. And nu bar will have a -1 only if it is nu mu. So I should write a nu mu. Otherwise, this reaction does not hold. Now, let us suppose that I don't know that there are two types of neutrinos. I will simply say pi minus is mu minus plus nu bar. Because I don't know theory. I am doing an experiment. I know there is a neutrino, anti-neutrino coming in this, but I don't know that there are two different types of neutrinos. I take this and I find that these antineutrinos are heavy, 10 to the power 14 neutrinos per second. How do I conclude? I check how many muons have come. Muons can be detected experimentally. They are charged particles like electron. I can count muon. So I know that there are 10 to the power 14 muons. That means there are 10 to the power 14 nu bar particles. So now, if I check that, I have written a note here. Note that with the introduction of muon neutrino and separate conservation law of lepton number, if I take separate conservation law that I discussed, it should read as pi minus is mu minus plus a nu mu bar. But I am not taking that into account because unless somebody does verify experimentally, I don't believe any theory. That's what we think now. So I will continue because that is why I have kept this note in a bracket. Having said that, what they did experimentally, these people, Liederman and this group, they took what is looked for a process. If you take a nu mu bar plus a proton, will it give you a E plus plus neutron? Why they do that? I will come back to the story and explain it to you. What did we do to detect an antineutrino in an experiment? How did we detect antineutrino? Sorry, discovery of neutrino. Remember the story. We took discovery of neutrino is done by this. We had a process, neutron going to a proton plus an electron plus an antineutrino. We didn't have any suffix for this. This is what is a process. Then I wrote again, there is a crossing symmetry relation, crossing symmetry process, which is possible, that is proton plus a nu bar, proton plus a nu bar goes into a neutron plus a E plus. This is a crossing symmetry relation called inverse beta decay. So from beta decay, I write this crossing symmetry relation and I take protons are everywhere. I take this as a source of nu bar. I take this as a source of nu bar. Where is the source of nu bar? Keep any nucleus decaying into a beta decay, there is a neutrino, antineutrino. That antineutrino interacts with a proton and it emits a neutron plus E plus. Now, suppose I have two different types of neutrinos. This is the story. Story ended. We checked all these processes in an experiment. So we concluded that neutrinos exist. I discovered experimentally. Now I want to check if there are two different types of neutrinos. How do I check it? Two different types of neutrinos. I will check it now. What do? I will take a, okay, let me go back and tell you, or otherwise, okay, let me take a mu minus, pi minus, decaying into a mu minus plus a nu bar. Okay, this mu bar, I assume that it is the same as the nu bar that I have written here. Then I use this as a source of nu bar. So I keep a pion decaying into a muon plus nu bar somewhere. And then I send this new bar and check P plus new bar. I should get a neutron plus E plus. Will it happen? Is the question. Do you understand what I am saying? I repeat. I know that a source of antineutrino is nuclear beta decay. If I keep a source which is emitting beta particles, there is always a new bar. I took that new bar and sent it into a Savannah River reactor, and then I noticed that there is a neutron plus E plus decay, E plus gets merged with a E minus, giving you 2 photons, and I found double pulse detection. This is a story of detection of neutrino, done and over. Now, how do you say that only beta decay is a source of antineutrino? I will take some other process which happens in nature, that is pion decaying into a muon plus a antineutrino. That is kept as a source. Instead of beta decay source, I keep source as my pi minus, which emits a antineutrino. And I want to check if this antineutrino, when it is sent into a Savannah River reactor kind of a setup, do you get neutron plus E plus? Question now is, I keep a source, I change the source. What will happen? Now, for example, I have a neutron going into a proton plus electron plus nu bar. This is my source 1. Pion decaying into a mu minus plus nu bar. Both are giving you neutrinos. Source 2. I keep source 1 is kept, and I have a whatever is the setup, experimental setup, where I have proton plus I send nu bar. That is what is entering into the system. I check E plus plus a neutron. This happens. I have verified. Now you keep source 2. What matters to you in your setup, your experimental setup, it has a proton and you are sending a nu bar. Do you get a E plus plus N? Do you have an answer for this? If source is changed, what you expect is only neutrino is coming, antineutrino is entering into your setup, you should get same process happening. Do you think that it will happen? I would say
Or it is
pion
less
also
probable.
is decaying. Pion also decays into the same kind of a neutrino. We already theoretically said lepton number conservation says pion decays into a nu mu bar, nuclear beta decay has a nu E bar. If both are same, this should be happening. This should happen. If these two are different, I don't find this process because this is a different kind of a neutrino. One process is already verified. In other process, I am sending a nu mu bar. Here I have a nu E bar. If I send a nu mu bar, what is lepton number here? Now we can check lepton numbers. What is L mu? Left hand side. L mu for a proton. Lepton number, mu-ness for proton. What is mu-ness for proton? Is proton a lepton?
0, ma'am. No, ma'am.
It's
0.
not a lepton, so it is 0. Nu mu bar. What is the L mu value? Nu mu bar. What is the L mu value?
-1.
-1. For nu mu, it is +1. Nu mu bar, it is -1. Equal. What is mu value? L mu for a positron. L mu for a positron.
0. 0, ma'am.
So this process cannot happen. Neutron has 0. It cannot happen. So you cannot expect to see a E plus and N and a double pulse kind of a process when you keep this. If neutrinos are different. Experimentally, a experimental setup is clever enough to detect if you have sent me a electron neutrino or muon neutrino. So that is the experiment. So experiment is they looked for the process. the experimentalists looked for a process, nu mu bar plus P gives you E plus plus N, where nu mu bar is from source 2, that is muon decay source, pion decay source. No such events were detected. So you are sure that if nu bar is same in both pi minus decay as well as a neutron beta decay, then you should have seen E plus plus N, but they are different. So it doesn't happen. So I can say that, oh, my conservation law wins here. Lepton numbers are different for muon, electron muon, and a electron neutrino and a muon neutrino. So according to a muon lepton number, how do you explain it? According to muon lepton number conservation, one should have nu mu bar plus P. If you take this, I will get a mu plus plus N, not E plus plus N. Mu plus plus N should be seeable, not E plus plus N. If you write a mu plus here, lepton number conservation holds. So this experiment, Brookhaven experiment, ran for several months. They wanted to know if you have two different types of neutrinos or no. They did this experiment for several months. Out of 3.48 into 10 to the power 7 number of neutrinos from the decay process pi minus nu mu bar, that is how many neutrinos that they sent in, that is how many mu minus that they detected. So if they have so many number of neutrinos, they found a total of 51 events of mu plus plus neutron. This process is seen, 51 events. I had told you it's a weak interaction, very some out of 10 to the power 17, only 51 number of neutrinos could give rise to mu plus plus N. That's what was seen. They occurred. So you do know that this does not occur. First process does not occur. Second process occurs, which confirms that there are two different types of neutrinos. I will stop with this. This is the experiment to show you that two different types of neutrinos exist. A little further, if I had only one kind of neutrino existed, then both these, that is, I have nu bar plus B going to mu plus plus N and nu bar plus P going to E plus plus N, both would have occurred according to lepton number conservation if I did not introduce a LE and L mu. These two are different according to us, but if we don't have such a distinction, lepton number conservation, pure lepton number conservation wise, both the processes should come. It doesn't come. So the absence of second process gives a clear confirmation for two different types of neutrinos. That is your process. Okay. So this convinced physicists that a second type of neutrino indeed existed. This gave 1988 Nobel Prize in Physics for these three people. These three experimentalists got Nobel Prize for detecting that there are two different types of neutrinos. There is a whole story behind this. Particle physics is interesting because we want to ask deeper questions about what is our nature made up of, how physics can explain what kind of particles can exist, what cannot exist, etc. So this is the Brookhaven experiment. And I only tell you one more link to this lepton family. I am ending the story of leptons with this class. What I am trying to say here is, now onwards, we will only continue with interaction of strong interaction, basically. So I will only say that leptons have been identified, and leptons are two different families is what we said. In 1962, lepton family had two generations. One generation is nu E, E minus, nu mu, mu minus. And same way, you have anti-leptons, two different generation of anti-leptons. But then anti-leptons, okay, fine. So then we have next 14 years, we had only two generations of leptons. But after 14 years, in 1975, there was another experimental discovery which said there is another heavier electron called tau minus lepton. It's called tau lepton. There is a tau lepton and its neutrino. So it comes with its own neutrino. there are experimental evidences for this. That is the end of the story as far as lepton is concerned. That is, we have three different generations. First generation, I have nu E, E minus. For nu E, E minus, I only have a lepton number for electron, it is 1, but L mu is 0. L tau, I have to introduce one more lepton number now because there is a tau minus particle detected. So these three generations are written like this. Nu mu has Le0, nu mu has L mu 1, nu mu has L tau 0. It has to be understood in this particular way. So antileptons have also same kind of role to play. So now I have an assignment. You find it in your, this has been already shared with you. Have I shared these notes with you? If not, I will send it to you again. This is your assignment. Find which of the following processes are allowed and justify your answer. That is why it is not happening, why it is, how you justify that it's happening. This is concerned with lepton number conservation. So please do this, keeping in mind lepton number conservation is being questioned. So that is what I have for this class. I will end this class now. I wanted to complete lepton number story. Now we will continue with strong interactions. Basically, what kind of a rules that give me arrangement of hadrons, baryons, and mesons. How do I arrange it? Leptons are arranged. Do you see that leptons are arranged already? It is the arrangement of leptons is this. I have only 3 generations and there are 2 electron pair, electron and electron neutrino pair, mu minus and nu mu, tau minus and nu tau. So my assignment to you is to check those things and search Google to find what is the mass of mu and what is the mass of tau particle. Electron mass, muon mass, and tau lepton mass. All 3 you have to list for knowing what are the masses of these particles, and tell me in MeV. That is my next question when I take your next class. What is the mass of electron in MeV? What is the mass of muon in MeV? What is the mass of tau lepton in MeV? That's what is my next question. And you should have answered these questions, whatever are given here. Okay. So that's all for today. If you have any doubts, you may ask me now before you leave. I know that you had so many classes, but I can't forego my class. So I had to take your class. So you may ask me any questions.